Hi, everyone. One of the main themes that runs through the thermochemistry unit in Chemistry 30 is to determine the enthalpy of a reaction. So we're going to take a look at the different ways that we can calculate enthalpy or determine enthalpy in a chemical reaction. First of all, we have communication forms, and that's where we're either given a value for enthalpy or it's a published value in a table. Or we can have the energy embedded directly into the chemical reaction. Another one is the delta H notation, energy written off to the right of the reaction. Or we can see a potential energy graph. A second method is calorimetry. And this is where we use a device to measure the energy that's transferred between the water and the chemical reaction. Here we'll use this formula and see that MC delta T represents the water in the calorimeter and N delta H represents the enthalpy of the reaction. And the third way is Hess's law. So Hess's law, we either have a series of equations that we add up and that gives us the enthalpy of a net reaction, or we have the formula. And the formula shows us the difference between the enthalpies of products and reactants, and that gives us the enthalpy of the reaction. So with these different methods, we can take a look at a number of diploma questions, and those diploma questions will illustrate some of these types of calculating enthalpy. So first of all, we have this question, and we are asked to determine the molar enthalpy of the reaction for nickel 2 oxide. So let's take a look here. First, we see that this is an exothermic reaction, and we know that because the energy is written on the product side. And we also see that the nickel 2 oxide here is shown with 3 moles. This means that the enthalpy that's released in this reaction is for the 3 moles. If we want the molar enthalpy, we'll need to take this value for the whole reaction and divide it by the 3 moles of the nickel 2 oxide. Now this, you can see, gives us negative 318 kilojoules per mole when we look at the units, and that's exactly what they're asking us. We can also see that these two values could have been eliminated immediately because they're endothermic. Okay, let's take a look at the next one here. And this time, we see that the enthalpy is given to us in delta H notation. And that's relative to the molar amounts that we see in the chemical reaction. Now they're asking us to find the mass of methanol that burns to produce this specific enthalpy, 9 times 10 to the 4 kilojoules. But they would like to see the mass recorded in kilograms. So what we'll do here, first of all, is we know that we need mass. So let's start with the molar mass of methanol. So we have 32.05 grams per 1 mole. And that's when we add up the carbon, the hydrogen, and the oxygen. But we only want this gram unit. So we need to cancel out moles. Now we know that there are 2 moles of methanol reacting in the equation that releases the 1275.8 kilojoules. This allows us to cancel the moles and then multiply by the energy that's released in the reaction, and we'll cancel the kilojoules there. Then we multiply that through, and we'll see our answer is in grams of 4,522 grams. But if we express that in kilograms, we get the 4.52, which we would enter as our 3-digit answer in our numerical response box. Okay, let's take a look at this next one, and it asks us to use this information box for the next 2 questions. And first of all, the energy released originally came from, now we know this answer to be the sun. And in the second question, they're asking us to choose a potential energy diagram that represents the reaction at the head of the match. So first of all, we know that this is a combustion reaction, and if that's the case, it's exothermic. So if it's an exothermic reaction, we need to see that the products have less energy. So our endothermic graphs we can cancel out. Then we can see these exothermic graphs are the same in every way except for the enthalpy. Now, the enthalpy greater than 0 is endothermic. The enthalpy less than 0 is negative or exothermic, so we need to choose C in this case. In this next question, although it does apply to 2 questions, we'll just take a look at this first one. And we want to determine the molar enthalpy of combustion for sucrose. In this case, they give us calorimetry data, as we can see here, the mass of the water, the temperature change, and the amount of sucrose. So we'll go right into our calorimeter formula, and we'll rearrange that to solve for the molar enthalpy. So let's plug in our values here, remembering that the MC delta T represents the water, but I'm going to change it into kilograms and show the heat capacity for water is kilojoules per kilogram degrees Celsius, because I want to get a molar enthalpy in kilojoules per mole, as we see in the answer choices. And then we'll divide by the amount. So our units will cancel, kilograms, degrees Celsius, and then we'll be left with the units of kilojoules per mole. So let's go ahead and plug that into our calculator. And we get 0.25 times 4.19 times 55.5 divided by 0.015. And we get 3,876 kilojoules. So you can see that rounds up to 3.88 times 10 to the 3 kilojoules. And this is also per mole. Next, we'll take a look at this question here, where they give us the reaction, but they don't show us a delta H or an embedded energy. And when that happens, we know we have to use Hess's law formula, because they're asking us for the enthalpy change for the reaction. So let's go ahead and do that. We'll start with the Hess's law formula. We'll get the pen here. Hess's law formula, which is the sum of the energy, the heats of formation of the products, minus the sum of the heats of formation of the reactants. So first of all, let's start with these products, and we can see that there's 1 mole of carbon dioxide, and we don't include the hydrogen because that's not a compound. And then we'll subtract the reactants. 1 mole of methane, which is negative 74.6, and 2 moles of water vapor, which is 241.8 negative. So we have to subtract the sum of the reactants, and we'll put that in brackets. Now, in our calculator, negative 393.5. And then we'll subtract and open the bracket, negative 74.6 plus 2 times negative 241.8, close the bracket, and we'll see that we get 164.7 kilojoules. So we can rule out these choices. We have that amount of energy for the whole reaction. And then lastly, it says, what is the enthalpy per mole of hydrogen? But we can see there's 4 moles of hydrogen, so we simply divide this value, our 164.7 kilojoules, by 4. And when we divide that by 4, we can see that we get the 41.2. And that's how we calculate.